park there, it's just annoying.
So.
Do they come out this?
Yeah. I have a lot of stuff too. I have more. Yes. The last route, it was like these two, it was like a 5-6. And so you want to like, we did it just so it was like up from one other guy.
This kind of 15 months.
Yeah, like 5-6.
I'm good with it. What's up? All right. Already. You got it. Yeah, that's but you know, as you started, you get all of that is like going across the word and like for this 20%. That's good, right? Yeah. Like learn there. That's spot on my hand. Yeah. You're talking as well. Yeah, no, there's this color. Remember, and Dawn's supposed to be like, I do that. And then. Yeah. No. They don't learn. So
Are you talking to that microphone?
I feel like if I don't too much, like, I think it was pretty good. I'm very sorry.
Thank you, sir.
I got it. Yeah.
That's weird.
Okay. Hello.
Yeah.
Good afternoon all. Yeah, today we got another presenter, and we can say it is ours. It's part of us. He's got his bachelor in Peru in mining engineering. He's also got his master's in mining engineering, Colorado School of Mines. He's a PhD candidate, almost at its tail end. I can say at the exit end. He's got 4 years experience in mine planning, underground, and he's also an expert in research in mining as well. Of course, everybody knows Lee is one of the most brilliant students right here. Now, ladies and gentlemen, let's put our hands together for me, Zamalloa, our presenter today.
Thank you all. Can you hear me?
Yeah.
Also, working actually.
It's not working out. I don't know what I want to do it, but
Well, let's just keep on with this. I'm going to raise my voice a little.
okay.
All right. Yeah, I want to apologize. My throat is, well, has sustained heavy damage over the weekend. Never mixed cold water with the jalapeno sauce. Really bad when trouble. Anyway, so what I'd like to talk with you today is basically over my research, my PhD research that hopefully I will be defending by late November. It's very directly related to the implementation of this not that so novel technology. This is well known so far, but it's just a different way to use. Is artificial intelligence methods that is not in different than statistics from a different approach on one problem that has been on the mining industry just on a recurring way, going back and forth related to the control of the fleets. In the past, 1980, it was called dispatch systems or truck shovel dispatch systems. Nowadays, everybody call them fleet management systems or the former jigsaw systems. The basic is a computerized system to make best use of our fleet, truck shovels. It is not exclusively for open pit mining, but also for underground. So the methodologies, the approaches are really similar. Let's focus on the open pit aspect because it is the most representative and it's really easy to understand what is behind. All right, so if we go back to 1947, Alan Turing said something that is relevant today more than it was 70 years ago. That is that what we want is a machine able to improve its thinking by recurringly repeating and processing the exercise over and over. So back in the time, it was like something out of any logic, completely science fiction. Nowadays, we call it artificial intelligence. So if we have the possibility to let the machine learn from its own instruction, from its own processing, then we're going to have a resource powerful enough to imitate human behavior. In the outline for this presentation, I would like to go over what a fleet management system is. Just for those who are not familiar with the topic. We're going to evaluate how this problem was approached 40 years ago and how it is nowadays. Then I will cover a simple example of why this problem is still so relevant nowadays and propose a simple methodological proof of concept problem. So we can see how this relation between the truck shovels and the dispatching, human dispatcher is. And finally, what is the methodology? How I would like to present these regression algorithms, multi-output analysis, and how we can make use of these simple mathematical approaches to solve a problem that is difficult to approach. Since the data we need to make this a feasible model is restricted and it is big enough, it's feasible or possible to solve. So the fleet management system of improved systems are spread all over the world. Wherever you go in any continent, you will see any mine, big mine, already implement these systems. We can see North America, South America, Africa, Australia, Asia, but these systems are working. But at the same time, we also see that the systems are not working properly. The fleet management systems are meant to make the best of the resource, across the shovel. But if I go to a mine in America, I will see a shovel waiting for trucks. If I go to China, I will see trucks queuing at a shovel. This is not supposed to happen, but it happens. And the source of this research is explaining why this happens, why our highly modified, complex dispatch systems are not able to account this problem, why it happened, what exactly is occurring in the background. That is basically explained at the uncertain nature of the mining operation. something we cannot predict upfront, something that will make a small modification in the operational parameters, but big time, make the dispatch system make incorrect decision. So the fleet management systems offer a good solution for the truck shovel allocation problem. Say this shovel needs this many trucks to work at optimal conditions, or this is how you must arrange your fleet, make the best use of your resources. You can meet production targets while keeping the operational constraints met, or to have your grades and your processing facility at the range you want. And ultimately, all these objectives are preset. That means that they are decided before for a long period of time. This is, for example, for an operation in Nevada, they decided that the most important objective is to minimize the fleet cost. That objective will not change over a period of time. That could be a week, a month, semester, a quarter, a year. So this is fixed, and this is something that is not changed over time that easily, if not by the dispatcher, by the short-term planners. If we go back to 1986, and the first approach to computerize this problem, it used to be solved by hand. It was when, let me close the table. Okay, sorry about that. It was by Walton Olson that presented the first computer dispatch system that took this huge problem and subdivided into a smaller. First was solved the decision to assign how much material should I assign to each shovel, or the same as saying how much material should I assign to each of these roads, how much material they can sustain for a logical transit. And this was a linear problem, really easy to formulate and to reach complexity if solved through a computational solver. And then the second stage was the dynamic program. That means if I have this capacity for this shovel or this road required to be filled by trucks, which truck should I send at a time to this destination? So I can have my fleet moving, so my trucks wait for an assignment and being assigned each time. So my shovel should not be waiting for trucks, and my trucks should not be queuing or waiting, just wasting more fuel. Now, this is not a flawless approach. This traditional approach usually is based on the snapshot of a mine. So the system is there, and when something changes or a decision needs to be made, it takes care of what is happening in the mine. So I will have there my shovels available, my trucks available, my roads available, and I need to deliver to each destination. It could be a waste dump, it could be a stockpile, it could be a processing facility, bleach pads or mills. Then the decision of how much material to be assigned is done. Then my truck, the allocation of the trucks is complete. But what problems are not accounted in each case? One of the major problems that is not counted neither at the beginning nor at the end of the calculation is the status of the fleet. What happens if there are some conditions that are restraining my fleet? For example, roads blocked, or changes in the weather that is preventing my trucks to perform as best as possible capacity, or conditions that are restraining my shovels to operate at optimal capacity. There are many conditions that are usually not evaluated by the software, but this is the reason why we have a human dispatcher, a human controller, the person who is sitting in the control room with 10 different screens and 4 radios, communicating, solving, accepting changes, giving orders, accepting exceptions. So all these problems are solved or actually solved by a human controller, a human being. And because this person is a human, there's a small possibility, not that small, that this person at some point will commit an error, because the level of multitasking of these people is over 10 hours straight for a full shift. And at some point they will start having distractions and they will start making suboptimal decisions. Shortcomings of the fleet management system. The first and the most important is that, for this is more for managers, that at the end of the quarter, when we evaluate what was the scheduled or forecasted production, it is different than the real. The reals are not meeting the same number. They are not matching. And it becomes a question, why? What was the problem? What is specific condition prevented the mine reach completion of those targets? There are many reasons. One of them is the dispatch. Then the conditions are not fixed unless a human being steps in and makes the corresponding changes. These dispatch systems, computerized dispatch systems, are incapable of modifying themselves because that's how they are programmed. They receive information and they process. They don't adapt to these uncertain conditions. So common at mine. And if we have these continuous problems accumulating over and over, at some point they will start making incorrect decisions. And in most cases, because these dispatch operators will visit any mine in the world, or most of the mines in the world, and we ask the dispatcher, what was your activity before being a dispatcher? I'm pretty sure that 90% will say I was a shovel operator or a truck operator. These are not people that have studied dispatching, and they are not people that have studied dispatching. They are people familiar enough or familiarized with this grid management system. And for that very reason, they know the technical part, but they don't really have that level of expertise in the background. They are not operational researchers or these mathematicians. And because this lack of knowledge, they don't really have the capability to explain why the software sometimes makes decisions that are not supposed to be the optimal ones. And if we don't really put the correct importance on this, we are going to start having some really weird scenarios. So this is something that you can observe when you let the dispatch system work without supervision. It will start trying to have a big problem. That doesn't mean that there will be the optimal condition. It will just try to have all the shovels working, all the trucks working, without considering that that is not necessarily the optimal case always. Correct. So I have a good example for you. This is my real case, real scenario. I one time visited a mine and I saw this problem. Some context behind this mine exists. This in the US. Is controlled by a really important operator. The dispatcher at the moment was a lady, 10 years experience, plenty of expertise, really nice lady. She was pretty familiar with her work, all the credentials. And around 10 a.m. in the morning, this happened. She was in charge of the northern part of the deposit. This mine had two pits, pit in the north, pit in the south. This happened in the north. In the north, there was 2 shovels operating, 6 trucks on one, 5 trucks in the other. At this moment, both shovels were overcharged. That means that each shovel had more trucks that they need to be operated constantly without pit per truck. 10 a.m. in the morning, one of the shovels failed, and the operator reported the shovel is offline. That's it. The dispatcher had a fraction of a fraction, but maybe 5 seconds to decide what to do with those 6 trucks. Well, many conditions can be evaluated. Maybe send some of them to the shop that was already workshop. Don't lose, don't forget that condition. Or send them to the parking area. Why do I need to have trucks moving if they are not going to produce? Or maybe send them some to the fuel mill. Most mines consider that after, if the given truck has less than 30% fuel tank remaining, they should refuel. Or maybe send it to the southern area, where the other dispatch that was controlling the southern pit was asking for trucks because his shovels were on the truck. So these conditions were available. What was the condition? What was the decision made by this dispatcher? It was this. She decided to send trucks to the other shop, although it was already on track, and the other 3 to the south area. Now, what consideration to remember here is that the other pit was 1 hour away from the northern pit. Having the truck there was the same as not having the truck for the rest of the shift that ended around 5 p.m. in the afternoon. So she was pretty much decreasing her available heat from the original 11, just 8. Now, and the maintenance crew was sent to the shop to evaluate what was happening. 15 minutes after the maintenance crew arrived, they identified the problem in the shop number 1 was an oil spill. And they said, we're going to check how we can solve this problem. And 15 minutes after, they managed to fix the problem, and the shower was back online. So the dispatcher needed to make a new decision. How she rearranged his fleet to continue until the end of the shift. The other 3 trucks to the south were already gone, halfway to the south. So there was no option to ask them to come back. And this was her decision. She decided to split the fleet and keep 4 trucks working in shovel 1 and 4 trucks in shovel 2. Now, with this new arrangement, both shovels were now on the truck. That means that neither of them were going to be able to complete the production target. They were supposed to by the end of the shift. So there were some difficult conditions that were eventually affecting the completion of the targets. And now what she had to do is make the best possible decision based on her expertise, her experience, and her intuition. And these 3 conditions are not necessarily in that order. And it depends a lot on the capacity, on the training, and the type of person these dispatchers are. Not all of them will have the same expertise to make this decision. Others may have completely sent the hose to the other side, the south pit. So this is a viable condition that right now is managed by humans with all the problems that is. Now, what can we do to fix this problem? What if this dispatcher knew that for that shovel, it was the failure mode that suggested that 75% of the cases the shovel was down was because of an oil spill? What if she knew that whenever there was an oil spill, 80% of the cases the problem was solved within 15 minutes? Well, maybe knowing this information, she could have made a better decision. But there is another problem here. This decision is there. There is no mind who does not keep control of this information. Every single mind has this data in Excel files, in MySQL data servers, but they don't really use it. And if they use it, they are arranged in a way that it's really difficult to find them, to process them, to make a decision within 5 seconds. That are those 5 seconds the dispatcher had to make that decision. But what I'm proposing is to find a system able to do this whole thinking to assist the dispatcher. So the dispatcher doesn't need to keep looking for this data, but have a side screen where she can see this and know upfront what should be done next. Okay, so that was the example from a real condition. Now, what we have next is how we can formulate this problem in a mathematical way that can explain with these algorithms. So when we start evaluating these formulations, this is what we see in a map. We have 2 shovels shifting waste material. We have 2 shovels producing all material. Each of them has the destination. The waste shovels are sending all the production to the waste dump. The old shovels are sending all the production to the mill. This is a specific problem for this proof of concept process. Each shovel has 2 possible roles, one closer and one longer. And that's actually something that many countries ask the open pit operators to consider. Always do accesses for any production area. Process for safety purpose. Not all the countries, but any of them. Now this is what we see. but this is not what the computer sees. This is what the computer receives this information. Just a simple schematic. When you define your resources, your shovel, trucks, and all the possible network of problems. This is what the computer will do. Some information about this example. The production capacity of the mill is 20,000 tons a day. For the wheat farm, we're required to split 25,000 a day, and each shovel is able to produce 1,400 tons per hour. So this has chart cubic shovels. And then we start making some decisions. This is for 10-hour period of analysis. When we start approaching from the operational research approach, we define an objective function, some parameters, and some constraints. For this problem, the decision parameter, the decision variable are basically to allocate the trucks, whether or not for each shovel, and more specifically for this problem, just to prove it, that if we cannot meet production targets, we are need to pay a penalty for not being able to meet each production program. And the objective function is aiming to minimize all those economic targets, but is we want to minimize penalties we're going to pay for not meeting the overproduction, the penalties for not being able to ship the required waste, and not the penalty, but the transportation cost of our fleet are related to the truck. Now, from a goal programming approach, that is the method that we operation research, that suggests that multiple objective functions can be solved at the same time, can be optimized together. But if you do this, there will be one operation function that is likely going to be more prevalent than the others. So that's why we assign this omega value that basically fits them. So we are weighting the importance of these models. One more problem is that currently traditional approach, regardless of the business system, MindStar, Jigsaw, Microplated Pro, Komatsu's, any commercial software you can imagine, they usually set targets, but they don't change the importance. Sometimes they turn on and off the importance, but they don't really label them. So that is one of the current weaknesses of these commercial packages. And that's one of the problems I would have to solve. And if we evaluate this correctly, the sum of the importance of all of them will always be 100 or 1. Now, let's start evaluating these undesired scenarios, discrete events that are not beneficial for our operation, that will diminish our resources, that will prevent us meeting our targets. So something that happens a lot in mind, like for example, roads blocked by a boulder, by a revision traffic, or shovels not operating, or trucks down. So you can see these conditions happening everywhere. What should be the reaction of the population to counter or to provide measures to prevent excessive loss if any of them happen? Well, sometimes it's not just one of them that's happening. Sometimes multiple events are happening at the same time. We don't just have a road block, but also at the same time a shovel down, and at the same time a truck down. For this specific example, I developed 22 combinations of this event, where at the basic scenario, nothing bad happens. Everything is nice. The fleet is working as intended. And for combinations, 2 events are diminishing our operation. You will consider that for this specific problem, we have 3 scenarios, 3 targets, 3 optimization objectives, and each objective will have a weight. What happens if we consider these weights as coordinates? Instead of calling them omega 1, omega 2, omega 3, call them X, Y, and Z. Well, because the sum of all of them make 1, we're going to have a 2-dimensional triangular plane. So for humans, it's quite difficult to see these multi-dimensional problems beyond the 3D dimension. This problem can easily go beyond that, 4, 5, 6. There are minds who work with 6 optimizations targets at the same time, but we cannot just draw a 6 dimensions cube, for example. So to make that easier, I took this problem and converted that to a ternary form. So 2D is much easier to evaluate. And this is pretty common, for example, in geology, evaluating the position of a rock, position of certain elements. But this time, instead of having elements, we're going to have optimization value. For example, the optimization of the penalties or deviation of ore production, penalties when you're not been able to ship enough waste, and the transportation cost. So this becomes a region analysis that we can start evaluating. Each of these points corresponds to the coordinate where all those weights converge. And we have the solution of the objective function. We can start creating these scales and these contours of global optimality. So this first triangle corresponds to basically a scenario, nothing but happens. That's why from the lowest possible point that is 0 deviation with respect to the best possible solution, global optimal solution, we're going to have a large area of decision. We can make many combinations and still be in the best possible scenario. But what happens if we start applying these discrete events? For example, I have 2 of the 100 contracts down. Then my ranges of decisions are extreme. And not just that, they are no longer convex, they are non-convex. And this makes a difficult decision because the weights will start behaving different. There will be some more prevalent than others. But we're aiming, or what this research is aiming, is to compute a way to always find this point in the best possible arrangement as far away to these contour lines, where any point outside is still a feasible solution. You can still have it moving, but you're going to pay more for exactly the same solution. So what we want to do is pay what is necessary to reach that objective. And this becomes more and more complex as we keep increasing the number of events, number of conditions under evaluation. Now, this is the proposed methodology. This is part of response to traditional approach. But before let the system evaluate the new formulation, we're going to skip and break that flowchart. And instead of doing that, we're going to redirect analysis on AI and artificial intelligence that will be able to analyze what is in the mind at the moment. So, depending on the event, we're going to have 3 possible scenarios. One scenario in which, by the rearrangement of the goals that mean changing the values of omegas, we can reach a better decision. Second, what happens if for one of those problems there is a probabilistic behavior? For example, a shovel is down. What if we know that there is a 25% that the shovel will be back within 2 hours? What if there is a 50% that the shovel will be back after 4 hours? What if there is a 10% chance that they will need to come back for the rest of the shift? So this is something real. We evaluate these data sets from the mine that are always collected by the maintenance department. We will see that we can actually model this probabilistic condition and make decisions based on them. And the highest level of analysis is the time-based parameter. What does it mean? Currently, the commercial software, all these approaches are basically reactive. What does it mean? It takes a snapshot of the mine, see what is happening, and solve based on that. They don't really see what's happening next. They are just reacting. What this problem proposes is if there are probabilities of events to happening in the future, then I can start making decisions today. For example, what if there is a considerable likelihood that one of my ore shovels will fail a week from now? Wouldn't it be nice that I start producing that ore that should will miss at some point today, so I can have the stockpile to continue feeding my plants rather than having like low grade ore blended or just keep the processing plant running. So all these apparently insignificant conditions actually mean if we start looking at the dollar and the dollar values, we were in the NPA of the operation, the OpEx of the operation. Once the AI has identified what is the best possible approach, then the problem is reformulated. Objective function is rearranged, and that information is sent back to the installed commercial software. So now a better decision can be made. So instead of letting each make this whole analysis over and over, let AI perform that, but independent to all the human errors associated. The problem will be solved, it is intended to be solved, and each time something happens, or each time a decision is made, all that data is sent back to the AI, so it can keep training the new conditions and the new responses. And if something changes, the system is updated. So this happens every time a truck requires a new assignment, new task. Now, because of time, we're just going to evaluate in the way. Yeah, I don't think we have more time than that. So this is the AI frame for the AI prediction algorithm. The first step is taking the data and evaluate all possible scenarios and understanding how the system will understand that an event is happening. For example, we said that we have several events, several discrete events. We will assign 0 if the event didn't happen, and 1 if they happen. So we are transforming a set of events to a binary combination. This binary combination, depending on the number of events, can be from 66 scenarios, 22 scenarios, to 100,000 scenarios. So this is a combinatorial problem and make this problem big enough to make it impossible to solve in a reasonable time. So the first step in this AI is to use a regression algorithm to make a quick and fast search. So this is the first implementation. Use AI to find the scenario. Second implementation is evaluate what is the case we're evaluating. Case 1, we said that it was when nothing bad happens. Case 2, when one of the roads was blocked, one of my trucks was down, one of my shoulders were offline. And we're going to solve for each scenario with a 10% accuracy what is objective function we can obtain for each. So we're going to have these scenarios for each case. And this is what we create ternary plots, those regions of participability. And here is where the second step of AI is applied. How we can regress the best possible arrangement of those goals from a coordinate system back to a weight or board priority-based for each target. And this is where the prediction AI works. And finally, send that optimal arrangement back to the formulation, the original LP. And each time a decision is made, that data returns to the system. These are the results. This implementation for 22 case scenarios. The inputs represents the occurrence of the events. 0 if the event didn't happen, and 1 if they happen. And they are given by predicted combination. Now, remember that we train the system with 10% accuracy, every 10%. But the predicted values are not 10% wide, but they are continuous. They are taking these ternary plots and finding the center of those non-convex shapes. And if we compare what was the global optimal decision computed with the solver, simplex, probably IDM simplex, that is the most common one, versus what was the new objective function computed from the predicted values, they are the same. Now, don't wrong evaluate that 100% accuracy means that the system is overfitted. That is not the case. What it means is that the point that was predicted is within that range of stability. What does it mean? If the regression model is able to find any point within this dark blue area, that is 100%, because it is meeting the minimum possible condition. But what we want is not just any point, what we want is the center point, the center of the best possible scenario. So that if a small change happens, even if the ternary plot ranges are modified, it is unlikely our decision will become small. Now, I'm showing you here for the first scenario, the results from 3 regression models. One corresponds to linear regression, that although create and is probably the best regression model for simple multi-dimensional regressions, but also does not behave well because this is a non-linear system. But still, for this problem, does a good job. The second is the k-nearest neighbor, that is really similar to the IDW system, where you weight based on the distance, the weighted average point. That also does a good job here. And the third one is the decision tree analysis regression model, that basically takes all the possible combinations and find what is the best possible output, the leaf, if we start subdividing all possible scenarios every 2 features. Now, when nothing bad happens, we have a large period of optimal feasibility. But if we evaluate a more complex scenario, when we have one or shovel down and one way shovel down, then my region of feasibility shrink, and they become non-complex. They multiply in 2. And actually, this one has the best possible scenario. This is one level above. Neither more pain, neither more cost. Now, once again, the linear approach tries to find the center. And it failed, because the center is not the best possible scenario. Here then was close to the core condition, but because this was non-complex, couldn't decide whether to go here or whether to go here. That's another problem of these regression models. When we apply them, we need to understand them. They are not a black box. They are not an equation that is impossible to understand. They have a reason. They use parameters that are performed for a certain purpose. So whenever we work with AI, it's very important to understand what the regression model stands. And lastly, the decision tree actually found the best possible arrangement. And that is the regression model selected for this research project. Now, there are not only 3. I actually evaluated 11 regression models, including last for reach, logistic, logarithmic, Gaussian, neural networks, and support machine. Out of these 11, only 9 perform more or less okay. Because although these regression models are available to market and are available open source, not all of them are fitting for the purpose of this problem. That is arranging a coordinate system. So it's important to understand that for everybody who does this sort of research. Now, with all this mathematical analysis, how can I arrange this data, this result, make it understandable for the dispatcher? They are not going to receive that data, those nice plot that says, this is what I should do. Instead, what we're providing them is a simple side screen where they will know the following information. This is happening at your mind. This is what you should, this is the new arrangement of active importance. This is what you should do. This is the new reformulation, and this is the expected outcome. Oversimplified, but more or less this is the result of the analysis. Long story short, what it's trying to say is, if this is happening at the mind, this is what you should do. Or if you make this decision, this is likely going to happen. Knowing that, the dispatcher will be able to make a much better decision. Really quick, the two approaches are basically performing this scenario. For probabilistic occurrence, we can evaluate simple problem, or shovels, all of them working the same system. What happens if one of the shovels is down and we have a probabilistic condition for the shovel to come back online at a certain moment of the shift? And this will represent that I still need some trucks, and having these trucks operating will return me value in the near future. If we evaluate them, sending all the trucks to the parking area, we're going to start keeping some of them, wishing that at some point this shovel will be back online. Now, how I should rearrange those trucks? I wait for this shovel to be back online, and there are probabilistic possibility that is something that is part of the analysis. The point is that minimize the cost that if the shovel is back online at some point, I will pay less for having a shovel close to that shovel, so it can go back faster and start moving material rather than ask the trucks go all the way from the parking area and waste time going back there. So there are multiple conditions that are evaluated by dispatcher, and this is one of the most recurring problems. The other one, looking at the time horizon, evaluate the possibilities of them occurring. So we have once again the scenarios, probabilities of them to occur at certain days, and then we can just run this simulation. One, if the event occurred, 0 if it didn't occur. And for a simple forecasted schedule, this is something we observe at the mind. But what we do is we observe them after they pass. What I'm proposing is doing it if they occur. So we can prepare beforehand, so we can minimize the losses. For this example, let's evaluate a hypothetical scenario where we're going to pay a flat cost, nothing bad happens. We're going to pay the same amount of money for all the periods as long as nothing bad happens. Nice scale. We always want to see this. But what happens if some of these events start occurring, start affecting the mind? Well, the traditional approach will try to overcome those problems. But because this traditional approach is not able to adapt to these problems, they will start paying more, just to keep the running. Now, we implement this adaptive approach. What we're going to have is that for certain conditions, without using more resources, we're going to be able to prevent that additional cost. Normally, we won't be able to do always best, because truth be told, the traditional approach, these commercial software are really complex, are really capable, they are really good, but they are not good for everything. What we want is to fill those gaps where they cannot find a good solution, and that will result in fluctuation that are the same as savings. So for the same resources, yeah, different arrangement, we will be able to pay much less for the same resource. We can make this, which will result in a large amount of savings at the end of the period, monthly basis for this problem. We're not making any huge change to our fleet, just taking different decisions, knowing what is likely going to happen. Some conclusions about the research project is that if I works, the AI does what it's intended to do. It predicts correctly what we want it to predict, the rearranging of goals. Second part is that it's highly adaptable. Why? Because what we did here in methodology is just make use of an instant FMS fleet management system and just run everything in parallel. So whether you take this to one mine in Nevada, or one mine in Brazil, or one mine in Europe, or one mine in Africa, it will just adapt to it. It doesn't need to be overfit the model. It will just use the data that is computed by this system, process it, and return a suggestion. So you can apply to any possible scenario. It's something that current systems are incapable to do. Lastly, because we are skipping the operational research approach, we're going to make these solutions faster and more accurate, as we are considering all these potential occurrences before they occur. So this is the research project. I will be happy to answer any question you may have. Thank you.
Okay, quick announcement before the questions. Deliberately, we didn't buy any food today. There's an SME barbecue outside. Immediately after here, we can get free food there. So we try to save some costs. Thank you.
Yes, sir.
Well, thanks for the presentation. Question I have is that CAT, also, that's always got that have the fleet management software, right?
Yeah.
How much do they have these type of capabilities to do the stochastic modeling? Because what you're doing is primarily stochastic modeling,
Yes.
and are they have the capability for discrete event simulation, or they don't, you know?
Okay, those are the questions. First, all the commercial software are deterministic in nature because they are responsive, they are reactive. Therefore, they cannot run the stochastic simulations because they consume a lot of resources, and that's something you don't want to see at the mine. This is something we do at the planning level, but not at the install professional implementable level. Okay, so that's a lot of stochastic simulation, but just for testing products. They never do that for the mine. In the mine, everything is deterministic, unfortunately. Hopefully, that's when it will be stochastic. But the computational resources are incapable. Do a stochastic analysis for each possible decision, considering that we make 5,000 decisions a day, more, less. For the second part, this software have these testing areas able to do discrete analysis, but they need to set up manually. So if some scenario needs to be set, the dispatcher needs to step in and start checking in, checking out, so they can account for those scenarios. But once again, for the automatic system, that is not the case. It's more like a training, testing, and analysis, but not for operational purposes. And I saw that for the hexagons, mine operated pro, but mine star works the same way. That's for Caterpillar. Okay. Is there another question? Yes.
Thank you, Lee. You said that you applied like plus 13 machine learning models and 9 of them gave good results.
Yeah.
And what's the results? You use the assembly model, or do you use the best score machine learning model?
That's actually a good question. Actually, when I defended my proposal, Dr. Wendy Fisher made the same question. And the answer is that these regression models have purpose. Linear regression does really good for these multi-output elements, that is coordinates. But for example, neural networks are not capable to do that because they require a large amount of data to be able to export data. But if you provide one feature, it won't be able to do it. So the result, the output will be values that cannot find a coordinate. Example, if for this problem we have coordinates or percents for each omega 30, 44, and also 30, 34, if we sum them all together, they make 100. Neural networks produce 10, 0.1, and 0.14. If you sum them all together, they will not make 100%. And that will also work for logarithmic, for Gaussian, and for SPR, that is super vector machine. So that's why not all of the regression models are fitting for this problem. Is there any other question?
So which one did you use?
I use primarily linear regression model. KNN, KNN, key stable, decision tree analysis. For further analysis, I'm also applying last linear regression, rich linear regression, logistic regression, Gaussian regression, just for testing purposes, random forest, and polynomial. That's what I'm applying. Is there any other question? Yes.
Wait, I have a commentary with my own experience. Right?
Yeah.
I think the problem, the main two problems with the dispatch system is one of them is what about the input that you implement in the system? Do you make before entering this information any simulation to avoid bias in the information? Because the system receives all the information and processes it, whatever the source of this information. Another thing is the system only gives you the best route, but no optimization according with the short and long planning. The idea for this system is implement all the information by manually, but they are not connected with the planning on the short and long term. And another system, the problem is the system is not integrated with the another system. For example, what happens if the geotechnical system detects some failures in the pit? Probably it's gonna stop part of the pit, but this system is not integrated with this. What happens if the one system detects some irregularities in the pit, and the dispatch is not able to respond with this new scenario? But have you integrated this concept in your project?
Okay, let's go one by one. First, with the bias condition. It's quite funny because this research is highly biased for the purpose of a given event. I didn't apply any simulation to this. Simulation software like Arena usually makes for real case condition, and basically you have your trucks moving at the same time. This approach is exclusively designed for one period hold. So this is not for real time right now. So doing that simulation is not of any use so far. Okay, so that's why this is highly biased. Biased to the occurrence of the event to happen. So it's more like a yes or no. For the second part that is really close to the first comment is to the changes in the pit. Something happens, something changes, and you don't know if the dispatch system is actually considering it. The answer is no. The dispatch system does not refresh by itself. What happens is that you need someone, a person, usually the dispatch analyst, who takes the map of the dispatch system and start closing roads if they are no longer available, or taking the trucks out of the list if they are under maintenance, or taking the shovels out of the list if they are offline. And if you don't do it, there is no one to make these minor changes. The dispatch system will keep thinking that nothing bad happens. Now, this process has been automated over time using sensors. There are sensors that can report the system automatically if one equipment is not working anymore. But still, this sensor, it will not change anything. It will just send an alert to the dispatcher to accept an exception that something changed. If the dispatcher does not approve that exception, nothing will change. The problem will still remain. And that's a huge problem when you have a communication issue. When your trucks move to areas where there is no LiDAR, there is no GPS, the truck is no longer receiving any data. This happens a lot with Caterpillar trucks. But if the system is not connected anymore, the truck will just keep repeating the last order until it comes back online to the internet of the mine. So the answer is the commercial software are not capable to self-update themselves right now. That is the problem, a huge problem actually. I think we're on time. There is one question, unfortunately nobody made, but I think it's important happening. The outcome is this approach, this research work able to replace human dispatchers? And the answer is not complicated to answer, but it's definitely needed for to discuss. And the answer is yes, it can. It is fully capable to replace human dispatching, but it shouldn't. And why? In 1979, IBM said the following: a computer cannot be held accountable for something that will impact human lives. Therefore, a computer shouldn't make this sort of decision. We will always need human dispatchers because humans are able to react to unexpected conditions, never seen before in aviation. So this approach is meant to assist human dispatchers, not to replace them, just to make their work easier and allow them to make better decisions. That's everything I have for today. Thank you so much. Thank you.
Let's have a person.
No.